In this video, I'm going to be continuing on with exercise 1.4. I'm doing the analysis. So in the textbook, all we need to find is these reactions. So I've already given you those values because those reactions have been found. And we have already found KQ and LP. We've already found those two. So what we're going to do now is we're going to continue and we're going to find KP this time around. Now, it's worth pointing out that so the reactions are shown. I've shown the reactions not as their totals, but I've shown the reactions as components because that's going to be easier. Also, that's how I had to enter it in when I wanted to check my answers. I used Johns Hopkins Trust Analysis software, and or it's a web browser. It's in browser software, so it's such a website. I've had to enter in those values that way, and I've broken this force that's being applied at member K, I've broken into its components. So I'm showing it that way rather than diagonals. There are some times, I'm actually a big fan of using diagonals. I think that there's definitely a place for diagonals, especially in the HSE where you can measure off the drawing, because the drawings will be done to scale and you can just measure off and you can take your distances, and as long as it's proportional, it doesn't matter if it's at 1 to 100 scale, 1 to 50 scale, or 1 to 131.75 scale. It doesn't matter as long as you take the dimensions off and you divide everything by the measurement on the paper, on the in millimeters, you should be okay. There's only been one HSC question that said it wasn't to scale, and I have it on good authority that the markers probably would have still given you marks for that if it wasn't to scale. There are times when they have questions that aren't to scale, and that's when the answer is that you should know those distances, like for things like threaded sections. In that case, they might show them not to scale, but typically they're going to be to scale. So what I've done here is I've needed to cut a section pane, and I have decided to cut, I'm trying to find KP, so I've got to find some way of cutting through KP. Now I could cut through KP like that. That would be insane. And the reason why that's no good is because cutting through KP like that gives me 1, 2, 3, 4 members. We really want to cut through only 3. 1, 2, 3 is good. Sometimes we only cut through 2. On the edges we'll only cut through 2. But 3 is what we're looking for. If we're cutting through more than that, we're going to have to do additional work. And that's usually beyond the scope of the HSC. So I've drawn this. This is the same two trusses. And I like to use the analogy of Gru and Vector stealing things in Despicable Me. They're going to steal half of this Warren truss, and they're going to use some drones, and they've named the drones KP, KQ, they've named the drones, and when they steal this half of the bridge, these drones are going to hold the bridge steady in place, or, just because it's such a daring theft, if they steal this half of the bridge, the drones are going to hold it in place. It doesn't matter which half of the bridge we steal. But what we generally want to do is we want to steal the less complicated side of the bridge. Now when I look at this, when I look at the two sides and I can actually compare, I'm not drawing the cut. Normally I would draw the cut. The reason I'm doing it is I'm going to solve this whole truss. So that's why I'm not drawing the cut. Now, when I compare the left and the right, the left-hand side looks more complicated. And it is. But these horizontal forces aren't going to matter. We're going to find out why they don't matter in a second. But it makes good sense to say, you know what, we're going to take the right-hand side because that's just, it's simpler. So what we're going to do is first of all, once we make our cuts, we're going to assume, and this is a pretty common assumption, that we're going to assume that these are in tension. Now, they might not be, but we're going to make that assumption that they're in tension. The reason I'm showing half there is that I can't draw this vector on the same line. Those two vectors are in the same line, they're collinear. So I'm just drawing a half arrow to show that I have a force acting in that same direction. It doesn't matter, but that's what we're doing. Now, so what we've done, let's go through our process. We're using the method of sections. It's the only thing we do in the HSC. Now, me and Snoop Dogg, we're the only two people who use method of joints. Everyone else uses method of sections, right? My mentor said to me, don't even bother teaching method of joints, or teach it to them really quickly and then move straight on, because method of sections is what we want to use for the HSC. The method of sections is way more useful when you want to find one specific member or two specific members, and that's what we do in the HSC. The method of joints is good when we want to solve the whole thing, and I might do the same video with method of joints later for those 2 or 3 people like Snoop Dogg and I who want to learn how to do method of joints. I actually like method of joints. I'm a correct weirdo like that. But for HSC, method of sections is your friend. Okay, there's kind of 2.5 steps, right, depending on the situation. So We could call it 3, but yeah, it's labelled like this. Okay, first thing we need to choose a section that we've cut through. We've already done that. We've said we're going to cut through this line, cut through 3 members. Then we have to ask, is it the meetup method or the lone wolf method? Now that will depend. That's not, you don't get to choose that. The situation tells you which one you have to use. Now when we look at this cut, we're going to use this side because it's a little bit easier. What we say is, okay, KP is our target. KP is the one we're going for. That's our target. KP is our target. And these are distractors, right? They're unknown, right? We've got these 2 distractors. So I've written them as others there, but it's distractors. Where does KQ and LP meet? Well, when we look at it, they're parallel, so they're never going to meet. So it means we can't use the meetup method. So what we're going to instead use is the lone wolf method. Now I try to remember that the meetup method uses moments, the lone wolf method uses sum of the forces. So we're going to skip to B on our options. So what we're going to say is sum of the forces in the x or y direction equals 0. We just pick any direction. To be honest, because we say x and y, it doesn't even need to be horizontal or vertical, but don't even worry about that. For the moment, we're going to say, in the HSC, it's always really going to be a vertical or horizontal force. Say, okay, KQ, let's think about this, right? So the obvious one, usually it's vertical forces. Not always, but usually it's vertical forces. Let's have a look. So we've got some vertical forces. We've got unresolved vertical forces. The sum of our horizontal forces is 0, right? 0 and 0. And if you look over here, the sum of our vertical forces, this and this cancel each other out. So in this case, we can be comfortable that what we're going to find is the sum of the vertical forces. So sigma forces vertically equals 0. And I'm setting the convention of plus up as positive. Now, if I like to draw a little diagram, I find rather than writing it mathematically, I find drawing a diagram way easier. So I've got 293.7 going up, and I have 225 going down. These don't need to be to scale, just indicative, right? And I've got a little bit left over. That little bit left over is going to have to be going down, right? Now, how much is that? I'll calculate in a second how much that bit going down is. But that's the process. That's how we're going to find this. Now, KQ, can KQ go down? Can't. Right? KQ only does horizontal. It doesn't have any vertical component. LP, same thing. So KP is the only thing that can deal with this problem. KP is the only thing that can step up. Now, because these are isometric triangles, we can say that this is 60 degrees. So I'm just going to write that in here, that this is all angles 60 degrees. Now, how Copeland would write this is Copeland would say, well, this force has to be going down, right? If it has to be, we need some extra down. How much extra down do we need? So we've got 293.7 minus 225 equals 68.7. Okay, so we've got 68.7 going down. KP has to be the thing that does that, right? It has to be. There's nothing else that can do it. Now you might say, what about this and this? Don't worry, because they're internal members, they're not being cut. We only care about external forces and cut internal members. So what Copeland would do is Copeland would write 0 equals 293.7. Now that's going up, so it's positive. Minus 225, because that's going down. Now, we made an assumption that it was in tension. So we're going to write plus KP. Now, it's not KP, it's KPV. But what we could write instead is this is what Copeland write. We'd write KP sine 60. And for some people, that is going to be how you want to deal with this, right? That's fine. If that's how you want to solve it, that's fine. So what we're going to say is that we know this number here is 68.7 plus KP sine 60. So if we have to move something over, so if we move this over here, if we're going to minus KP to both sides, we get minus KP sine 60 equals 68.7. Well, okay, so what we've got is a negative number, so we can write here, I don't know what showed up there, but that would be bad. Okay, sorry for that interruption. Okay, so this was negative. I'm going to give that a bit of a space. I'm going to say because this number was negative, that means our assumption was no good. So for our assumption, we assumed, we wrote positive here, right? We wrote positive because we assumed tension, therefore up. And because it was negative, that means our assumption was therefore no good, therefore not tension, therefore compression. Okay, so then what we can do is we can divide both sides by sine 60, and we're going to say Kp divided by 687 divided by sine 60 equals... Now I know sine 60, I can just write it as... I've memorized that as 0.866, what we like to call the disco number. 0.866 equals 79.3. My spreadsheet, my Johns Hopkins tells me it's 80. I'm happy with that. It's within one Newton. So Newton, and that is in compression. Okay, we just solved it there once. Now this time here, I'm going to solve it the way I would normally solve it. What I would say is, okay, well, we're going to solve it two different ways. So over this side, what I'm going to say is this. I'm going to say we have the sum of the forces horizontally. Sum of forces horizontally equals 0, right? 0 equals 216.5 minus 216.5 equals 0. So that's not our problem. So what we want is positive sigma forces vertically equals 0. What do I have? I have a imbalance, right? I have, I'm not even going to write the formula. I'm just going to write that and I'm going to draw my little picture, right? That's how I like to do it. For me, I'm happy with that as sufficient working out. I'm pretty sure that HSC would be happy with that, right? I've got 125 minus 56.3 equals 68. This amount here is going to have to be 68 up. 68 up. Now, the thing is, we assumed it was going to be going down. If we assume tension is going to go down, so it's obviously, so we can just write compression. Right? Straight away we know it's in compression. Now, if we know it's 68 going up, we can write here KPV, the vertical component of KP, equals that. So if I write KPV, and this is KP, what is that number going to be? So I've got 68.7. This is going to be 68.7 divided by sine 60. Right? Divided by 0.877, going to be equal the same thing. We get 79. Not very clear handwriting, but it will do. That's how I would approach it. That's how I would personally use the left-hand side method, but I know there are people who are going to want to use the right-hand side method. I'm probably not going to do this method more than once. This probably should be in blue. I wrote that, and just to say, I only wrote that in red to show that's how Copeland would do it. It's not how I tend to do it, but I'm pretty sure that's how his notes are written. So that should be in blue, as in, I try to only write red stuff is stuff that you, red stuff is stuff you don't need to write. That's how I try to approach it. Okay, so we've now found out, now it's in compression. Our symbol for writing compression, to me, looks like the letter C, right? For me, that looks like the letter C. Yeah, it's a bit of a wonky C, but that to me looks like a C. I just trained myself to see that as a C, and I've told myself that I just like to imagine in my own secret alphabet, this is going to be not my first secret alphabet, my second secret alphabet, puns at B, that looks like a T. So we're going to draw, now I generally draw red in tension, because just red seems inherently more tense, but unfortunately in this case, Johns Hopkins doesn't agree with me, so we're going to draw that as, and also by changing the colours it gives you too much of a crutch. So we're going to draw those arrows, and so the idea is here, it's really important to know, what we're saying is this side is pushing into the node, and this side is pushing into the node. I'm going to change this because we know that to be incorrect. We know that to be incorrect, so we're going to go like that, just to say we know that to be incorrect. Okay, so 79, our assumption was incorrect, and there's nothing wrong with having our assumption be incorrect, obviously. I'm just going to turn that sideways just to make it a little bit easier to differentiate, because we're going to be doing another one in a second, and I need to have space for it to go, and I like to write above the line. 79. Johns Hopkins said 80, but I can live with that. Okay, so what we're going to do next is we're going to do PR, the spin doctors. Okay, don't need that anymore. I feel as I already did LK. Is that possible? Yeah, I already did LK in my other video. I can't look at my other video. Which makes me think I haven't done this one. I'm gonna say that I've done LK, because I just look at it and I'm like, I'm sure I know I did LK. I'm getting that number. Call it 65, and it's 65 in... Well, okay, I could even try and figure it out just by looking at it. So I'm going to say, if this is pushing up, if I know RL is pushing up somewhat, and so this is where you can get marks just by getting the tension and compression. Often people are like, I'll just take a punt, tension and compression, 50-50 chance of getting it right. Well, if I know that RL is pushing up, that means that if LP can't push up, it's not capable of pushing up. So the only thing that can push down to meet that challenge of this force, it has to be going down, so it has to be in compression. So when I look here, it's red, so it's in compression. Yeah, it's 65. Yeah, that was the one I solved. I'm pretty confident. I don't know if I did. I'm going to do that one last. I might even do that one. I might do this one. You don't care. Okay, so what we're going to do now is, I said we're going to do PR. PR is close enough to the same thing. Now what I'm going to do is I'm going to set up my cut. And so it has to cut through PR in order for us to find PR. I can go here, that's an option. We did find LP, that's what it was. We did a cut like this, we did the smallest possible cut. Okay, for PR we can do a cut like that, and that's probably what we're going to do. Or we could take a ridiculously big and complicated cut to the right. We're not going to do that. We're not going to do that. A ridiculously big and complicated cut to the side. We're not going to do that. So what we're going to do is we're going to cut through here. And I said I wasn't going to draw the cuts, but here I am. We're going to cut through there, and I'm going to draw it now. We could do a cut like that. But there'd be so many forces to worry about. We've got a force here, and a force here, and we've got force here, and force here, and force... That's 5 external forces. Way too hard. Instead, it's just way easier if we just go here. Okay. RR, QR, PR. Now, I wanted to do the arrows in red to show that they're assumptions. But you know, we don't really even care which way QR is, because we're not solving QR at the moment. We're not solving QR. We're solving PR, and we have one unknown, QR. So where can we take moments about? Well, to solve QR, we have choice of Q or R. They're the only points that QR passes through. So it doesn't need to be the member itself. We can extend it out into infinity, but there's no other named points. Even if we extend this all the way down the board, all the way up, there's no other points that it passes through. P passes through lots of points. Right? It passes through lots of locations where we can take moments about, but for R, there's only really, for QR, there's only two points. If we take it about R, that's no good. Because if we take it about R, we're going to multiply everything by 0, so that's no good. So really, our only choice, I've jumped a step. So I've said we cut through the sections, we're going to use Meetup or Lone Wolf. Well, PR and QR, they both, PR can only take horizontal forces. RQ can also take horizontal forces. So PR is not a lone wolf here. PR is doing the same thing as QR. It's not doing anything special. It's not being a hero. So in that case, QR is going to meet up with nobody. Right? Now I know that's a bit of an odd concept, but that's the method we're using. We're using the Meetup method. Now this is a great opportunity for method of joints, but we're going to use method of sections because we're just going to be consistent. So we're saying, well, PR and QR, they both go horizontally, so there's no opportunity for Meetup. So what we're going to use, no opportunity for lone wolf. So what we're going to do is we're going to use the Meetup method, and we say, well, where did the others meet? So the other, in this case, is QR, and it meets at point Q. So we're going to take Meetup, we use moments, so we're going to use the formula clockwise sigma moments measured around point Q equals 0, 0 equals. Okay, so we've got three forces, right? First we've got QR, but we've eliminated QR by taking moments about Q. The perpendicular distance is 0. Boom, it's out of there. I do like to use black for the actual, I think I'm using blue for that. Yeah, anyway. It's odd sometimes. I'm recording this on my own, so sometimes it's a bit weird. But okay, so I've got 0 equals, and what have I got? I have got 0 QR times 0, and then I've got RQ, sorry, reaction R, and I've got PR. So I'm saying some odd things here. Now, what is the distance? What is the distance if we measured here from Q to R? So I'm going to draw that on the diagram. Normally I wouldn't, but, well, normally I would, but not when I'm solving the whole thing. What is that distance? That distance is 1/2 of a triangle. Now in other videos, I talked about how, we could call it like T, but the thing is those T's are going to cancel out. It doesn't matter if we use feet, inches, cropogs, cubits, hands, doesn't matter what you use, it's going to be, it all cancels out. So that's 0.5, and the distance from here to here is 1 sine 60, or √3/2, or I just have memorized that number as 0.866, which I call the disco number. Okay, so I'm going to run right into that, so I'm going to erase that now just so that I have some room. Okay, so R is how far away? R is 0.5, and is it going clockwise or anti-clockwise? I put my finger on our reference point. Our reference point is Q. I'm going to push R, and I'm going to push up in the direction of R. Anti-clockwise, so we keep it at negative. Okay, so now we're going to do PR, and we're going to push in the direction of the arrow. That's clockwise. Now, because they're different, and we only have two things and they're different, we know that our assumption was correct. So PR, and our distance is 0.866. So what we're going to have is, we actually know the value of RR, so I can write that in as 293.7. Okay, so we're going to bring this over here. We're going to say PR was 0.866 PR equals that number. I've got to type that in my calculator. 293.7 times 0.5 equals 14,147. There's percentages which I'm going to keep in my calculator, but I'm not going to write on the board. And then I divide both sides by 0.866 divided by 0.866 equals 170 newtons. Now, our assumptions, right? I didn't write my assumptions in this time. So we said that PR, we assume tension, and so therefore it's going clockwise. And I like to draw a little arrow to help me remember. Our answer was positive, therefore the assumption was okay, therefore tension. What were we doing? Oh, yeah, okay, it took me a while I was a bit confused while I was looking at, but we were right. And our assumption is correct, get tension. Okay, I was a bit worried for a second, but we're good. Now, I'm not even going to bother doing the other side. This other side, way too complicated. It's not even worth doing. If someone wants to do that for the lols, right, for practice, they could do this whole other side. But if they did this whole other side, they know that it'll have to be that same answer. Okay. Mark on my shirt. Anyway, okay, so what I'm going to do now is I'm going to find, I'll mark that on that board. Oh, I drew the wrong thing. I drew the wrong thing. It's going to be in tension. And tension, I mean that shape just looks more tense. Yeah? So, now, what we're going to do now is we're going to find RQ. Now we're going to use exactly the same cut, but we're not going to use this side because that would be ridiculous. So we're just going to clear this here, and we'll just use the same diagram because we're using the same cut to find QR. So with QR, what we have here is we have a situation where we have three forces. We have QR, which has horizontal and vertical. We have R, which is I don't know why you didn't just write this number up to start off with. An external force acting up, and we have PR, which is going horizontally. Now, in this situation, we do know now what PR is, and we could use that PR to say, well, PR is this amount of, QR is a lone wolf in two different directions. QR is the only thing that can balance PR's force here, but also QR is the only thing that can balance this force here. Now, both of those situations, QR needs to be going, if PR is going to this direction, right, PR is going to the left, well then QR has to be going to the right. If this external force is going up, that means QR has to be going down. So both of those forces mean that we can realistically, not just assume, but we can know that it's going to be going down. And that's in blue because that's not an assumption, that's something we've figured out just by looking at it. We can interpret this and say, that's not an assumption, that's something we can say with some degree of clarity. Now, if it's pulling from the node, it's in tension. If it's pushing into the node, it's in compression. So we can say this is in compression. How much unresolved force is there? Well, sum of the forces vertically equals 0. Right? We could use the horizontal force. We could find out the horizontal value of PR, which we just did, and we could actually, I will show you in a second, we could do that. But instead what we're going to do is we're going to say, well, QR has to be going down, and I'm just going to draw my diagram really simply. This way I can't get it wrong. So if I write 293.7, well, I'm then going to have a vertical component of QR, so QRV, or what Copeland would write as QR sine 60. Fine with it. That's actually a fine way of doing it. I just like to draw it a little bit more diagrammatically. So we're going to have to say that that's also going to equal 293 just to balance it. Well, if that's QR sine 60, we divide by sine 60 and we're going to get our answer. 293.7 divided by 0.866. I know what sine 60 is in my head. That's going to give me an answer. Therefore, if I write, I'll just write Copeland's working out here. If I say QR sine 60 equals 293.7, QR equals, and we've figured out its compression from observation, right? That's totally reasonable working out. That's excellent working out. I'm going to instead just draw it up as a little bit of a diagram, and I'm just going to say, well, this is 60 degrees. QRV equals 293.7, therefore QR equals, and I would say That's going to equal 293.7 divided by sine 60, which equals 293.7 divided by 0.866, which equals 339 newtons compression. Now I had a look at that before the screen switched off, so I'm pretty confident that's right. So it's compression, so I draw it like a C. Looks like a letter C to me anyway. Looks like the cent symbol. Anyway, you don't really need to know those symbols. I think that's more of a thing that's relevant at uni and workplace level when you're looking at these diagrams. Definitely at uni I think it's more relevant, but yeah, here not so much. I don't think you seem to use it very often in high school. I remember really struggling to memorize these symbols. Okay, so what I'm going to do is, I'm going to do PQ, because I really don't remember which of these two ones I've done anymore. I know I did a cut through that side, I don't think I did LP after all. But it's the same thing, I'm going to do that one through the method sections. We've got PQ as our last one I want to do today, or at least in this recording before I set up again. So let's have a look at where our cut is going to be. So we want to find PQ, and so we're going to cut something like this, right? Again, we could cut like this, we could cut like that, but I mean that would be ridiculous. 1, 2, 3, 4, that's too many, right? This way here, nice and simple. So we're going to cut through that. And are we going to take the left or the right? Now you could take the left-hand side, but I'm going to take the right-hand side because I know that will be simpler. And it's going to look like that. So I'm going to label my other forces. I've got KQ, I've got KP, which is the one we're finding, and, sorry, we're not actually doing that. We're cutting a little bit further. We're cutting here. Sorry. There you go, that's where we're cutting. Because we didn't cut through our member with that one. We're finding PQ, and we're finding PR. Okay, so let's label this is our target, PQ is our target, and KQ is an other, they're distractors. KQ and PR, they're parallel. So, okay, let's go through our steps. We've chosen a section. Now we're just deciding if we're going to use Meetup or Lone Wolf. KQ and PR, they're parallel. If they're parallel, we know we need to use Lone Wolf. Right? I'm not even going to go into any more detail. If you see parallel, if your others are parallel, Lone Wolf is the only option. If they're not parallel, well then you know Meetup is your only option, but we'll worry about that later. We sometimes have diagrams that look like this. And when you're told to cut these, right, people say, oh well that's an inside one, so that should be a Lone Wolf. No, because in this case, they do meet up. They meet up over here at that location. Yeah? So it's all about looking at if they're parallel or not parallel. That's the key. Okay, so what we've got now is we're going to use the Lone Wolf method. So what does QR do that the others don't? QR is not like the other members. QR is the only one who likes going vertically. So we know that we have a sum of our forces vertically equals 0. Now I could use the maths, but I said already that I don't like doing that. So what I'm going to do is I'm going to say 293.7, and Copeland would just write PQ sine 60. It's only sine 60 because we know this to be 60 degrees, right? Otherwise we wouldn't get away with it. I think it's easier just to remember, rather than doing the maths now, I say PRV, and so I say, well, PRV equals 293.7 down, and because it's down, our assumption is that it will pull out. If we assume tension, right, its tension will be down. It matches our assumption, so we can say, therefore, compression. Sorry? It matches our assumption, I'm sorry about that. It matches our assumption, so it's going to be tension. I do sometimes lose my flow in the time it takes me to unclip pens. I said I was going to write in black too. Anyway, so if I know PRV equals that, well, we could use the Copeland method where we just simply say if, it's not even PR, it's PQ. If I say PQ sine 60 equals 293.7. Therefore I can say PQ equals 293.7 divided by sine 60. Right? I'm going to instead do it this way. I'm going to say, well, we need to have a force down, so that's going to be going down. We already it's going to be going the other way. Okay, so if this is PQV, this is PQ, and we're going to say if that's 60 degrees, we're going to say that PQ equals PQV divided by sine 60. Hey, it's exactly the same as what we wrote here. So that equals 293.7 divided by 0.866. I'm not sure if that's my old number or not. 293.7 divided by 0.866 equals that number. Okay, and we know that it's in tension because we observed it. Okay, that's how we solve. I don't think I did that one, but I don't care. It's the same method as here. That's how we solve this using the method of sections. I'm going to record later, I will record how to do it in method of joints, but that won't be in this video.